All right, so first thing we went over in this unit, okay, was climate. Things we need to know, okay? We need to know the components of climate. That is temperature, precipitation, light, and winds, right? That's an easy multiple choice question, right? There's 4 options there. And then, of course, you need to know the factors. Okay, you need to know about latitude, altitude, mountain barriers, proximity to oceans, centers of high and low pressure, okay, etc. So there's definitely going to be some multiple choice about this topic. There is also a written response item about this topic. Here's how it's going to go. I am going to give you a location and a map so you know where this location is in case you're bad at Canadian geography. Okay, you will have to tell me what factors affect the climate at the location given on the test. Okay, and then tell me how those factors will make the climate the way it is. Okay, it'll be a place that you're relatively familiar with so that you can kind of illustrate your knowledge of the factors affecting climate. Everybody follow there? Okay, so you'll be given a location and a map, a location that you'll know at least relatively well, okay, and you'll have to tell me, here are the factors that affect climate. Here's the way the climate is going to be in that location because of these factors. All right, so you have to know them and you got to be able to apply them. Austin. No, you will not get a climatogram for the listed location. Okay. Second thing we went over, climatograms, okay? And we said yesterday when we talked about biomes that the question on climatograms will be, here's a climatogram, tell me what biome it goes with, okay? 2 marks for interpreting the climatogram, 2 marks for describing the biome, 1 mark for tying the 2 together. I mean, I look at the climatogram and I see a big bell curve. So I would say this is not near the equator. This area is very cold because the top of the bell curve is highest point is 5 degrees Celsius, right? So you looked at it and you were able to go, okay, I remember that the line on this climatogram is temperature and the bars are precipitation. That's what I mean by interpreting, right? You tell me what the climatogram says, talk a little bit about the biome, explain why they fit together. Does that make sense? Okay, third thing we went over, energy transfers in global systems. This is big because there's not a specific question necessarily about this, but energy transfers are kind of the biggest theme in this whole unit. So they are part of many multiple choice questions. They are also part of many written response questions. Okay? Being able to apply your knowledge of how energy gets transferred on Earth will be an important part of many of your answers. Okay, so we need to remember a few things. 3 things can happen to light when it strikes the Earth's surface. What are they? One of them is on there already. It could be absorbed, reflected, used. Okay, and when we say used, we mean what process? Photosynthesis. It strikes plants and they convert it into chemical energy. Okay, those are the 3 things that can happen to light. Okay, and how much of each happens is based on this thing, albedo. Okay, albedo is the reflectivity of the Earth's surface. Right now, our area has a very high albedo because the surface of the Earth is covered in white snow, which is highly reflective. Okay, a low albedo means that we absorb a lot of energy. Okay, so a question like that would maybe ask about this could be something that's just like flat out, explain what could happen to light when it strikes a piece of tropical rainforest in Brazil, right? And then you would say, well, since Brazil is near the equator, there's not a lot of snow, so the albedo is very low, lots of energy would be absorbed. There's also lots and lots of plants there, so a lot of that absorbed light is going to be converted or used by photosynthesis, turned into plant material, etc. Okay, everyone follow on that? And then you could maybe talk about the light that's absorbed or the energy that's absorbed will cause increases in temperature, could cause changes in latent heat, water to evaporate, things like that. Just explain when energy gets absorbed, where are some places it can go. Okay. All right. What are the three ways energy gets transferred? Conduction is one, convection, radiation. Okay. Do we need to know those? Yes. And you're going to need to apply them to a real world situation. Okay. So, for example, I might ask you, based on your knowledge of heat transfer, explain why a solar water heater would be dark in color. Okay, or something like that. Okay, and you would say, well, dark colors have a low albedo, which allows them to absorb a lot of radiation. Okay, which then makes the temperature go up, and then that heat can be transferred through convection in the water inside, because convection occurs in fluids. Get the idea here? Okay, you have to show me, I understand that radiation works this way, convection works this way, conduction works this way. Right? It's going to be a real world practical application kind of question. Okay. Usually it involves designing a structure that either captures or reflects energy, one or the other. Okay. So you probably want to talk about how things like insulation work. Okay. We showed that the day we went over that. Okay. We talked about how air gets trapped, and so convection can't happen because the air can't move, things like that. Okay. There's also the three parts of the Earth, and we should know their roles. Okay. And that goes along with, again, radiation, convection, and conduction. So the atmosphere is the most fluid part of the Earth. It's where the bulk of the energy transfer occurs because it can move most easily. Okay, that's where convection occurs. We call convection within the Earth's atmosphere wind. Okay, there's also latent heat involved in that. Okay, within the atmosphere, latent heat moves as moist air. Okay, moves from wind, moves by the jet stream. Is the jet stream something we should know about? Yeah, it'll come up later, but it's also something important. Right, the hydrosphere is all the water. Okay, convection is what transfers energy within the water, and the lithosphere's main role is to provide soil for plants. Okay, it does some absorption of energy. Okay, but for the most part, it doesn't transfer a lot because conduction doesn't transfer energy very well over large distances. No, convection and conduction are quite a bit different. Remember, when we were talking about conduction, conduction is particles are in a solid. Conduction only occurs in a solid. Okay, that are moving back and forth. They can run into each other, but they can't move past each other. Right, which is why solids are rigid. In a fluid where the particles are farther apart, they can start to move, and if they start to move in unison, you get a current set up. Okay, so there's no current in conduction. It's just a matter of, can the particles run into each other like an old-fashioned kind of like bucket brigade, right? They're passing the energy along from one to the next, whereas in convection, they're all moving together. Yeah. Convection is way more efficient at transferring energy. All right. So yeah, definitely know those three and their roles. Obviously, the atmosphere is the most important one. I think this diagram here that I drew was about how insulation worked. Right? It's all the fibers that crisscross, and the air gets trapped in the middle. Okay? The air can't move, so convection currents can't get set up. Okay? The other when I taught that lesson originally, I said, here's, if you have hollow walls, which no one has, but if you had hollow walls in your house, okay, you'd have hot here, cold here, okay? And because of the second law of thermodynamics, energy would flow from hot to cold. Okay, actually, sorry, it would go the other way. Hot air rises. Okay, so this air would rise. Air that's cold near the outside wall would move in to replace it. This hot air would come down here as it cools, okay, and energy would get transferred from the inside of your house to the outside of your house very rapidly. Okay, having the wall filled with insulation doesn't allow the air to circulate, so convection is prevented. Right? Conduction is also prevented because conduction can't occur through air, and there's a whole bunch of air spaces in there that essentially prevent conduction from occurring as well. Right? Can that stop radiation from occurring? No, it can't. Okay, it can't stop radiation from occurring, but what you can do is have the interior surfaces of your house painted a light color, okay, which would reflect radiation back into the house. All right, where are the places your house loses energy the most? Windows and doors. Okay, doors because they're thinner and don't have as much insulation. Okay, and usually they're not perfectly sealed, so there's going to be some convection out through them. And windows allow radiation really easily through them because they're transparent, unless you have like the low E windows. And obviously, because they're very thin, they're not insulated as well as the rest of your walls. I mean, if you really wanted your house to stay warm, you would build a house with no windows. Okay, that would be better insulated than a house that does have windows. Obviously, that's impractical. Okay. All right. Questions there? All right, then we talked about wind patterns after that. Okay, so we need to be able to explain how prevailing winds happen. All right, we talked about how that's a combination of convection and the rotation of the Earth. Okay, the Coriolis effect plays a small part in that. Okay, but for the most part, it's the rotation of the Earth and convection. So energy near there's more energy near the equator. So air there rises, okay, and cool air from above comes in from below, or sorry, comes in from above, okay, and then the Earth spins underneath it, which creates it, making it look like it. How about I show you the picture I drew, even though it's terrible. Okay, so near the equator, okay, we've got this convection current here where hot air rises. Okay, cooler air from further north moves in to replace it. Okay, and we get a convection current happening. Because the Earth is spinning while that's going on, this air here that's moving, that's trying to move directly north-south, appears to get deflected because we move into it as the Earth rotates. So it's a combination of convection and the Coriolis effect. Okay, what I would say is really explain why there's any movement at all. Okay, why is there movement at all? Because there's a difference in the amount of energy the world receives at different latitudes. Okay, talk about the second law of thermodynamics, talk about convection. Like I said, the Coriolis effect is a smaller part of that. Okay, we're looking more at the energy transfer part of that. Okay, we also need to know what the jet stream is, because the jet stream is important. Okay, if a question is asking you, explain how energy is moved from, the equator to more northerly parts of the world, the jet stream is certainly a big part of that. The jet stream allows large air masses to be moved, okay, by a means other than just by prevailing winds. In fact, it can override the prevailing winds in a lot of cases. Okay. Now, the jet stream is mostly concerned with latent heat. It's going to move those air masses that are full of moisture that contain all of that evaporated water, okay, that carries the latent heat with it. Right, and we saw the math of that a little while ago, right? Like we saw that 1 liter of water contains over 2 million joules worth of energy stored in it. To an extent, the jet stream is also just one of those kind of freak occurrences that's there. Okay, it's where its location is based on high and low pressure. Okay, but it's not necessarily because of convection and differences in energy. Okay, so there'll be probably a couple of questions about about this idea. There may be one full written response question about the Coriolis effect, so I'd understand how that works too. So is there a lot of explanation on this test so far? Yes, okay. Because there's not a lot of material in this unit, I expect that you can apply it more than you would in another unit. So there is going to be a lot of application of your knowledge here. Is there something wrong, Kai? Then we talked about specific heat capacity, okay, and one of the reasons why proximity to oceans is a factor that affects climate is because the ocean has a very high specific heat capacity, and that it's made of water. And that means it can absorb a lot of energy, but it can also give off a lot of energy without changing its temperature. So we need to know what specific heat capacity is, and then obviously solve problems using that formula. This formula is also going to be useful in what kind of question? In the latent heat question. Do you need to know that shape? Yes, you do. Okay, I'm not giving you that shape on the test. I'll give you the formulas on the test. I'll give you LF, LV, all the specific heat capacities that you need, but you need to know that water freezes at 0 and boils at 100. And you need to know the shape of that heating curve. You also then need to know, where do I use which formula? So we use E equals MC delta T anywhere T is changing. Okay, so anywhere where the line is going upwards. Anywhere where there's a state change is a flat line. We have to use the thermal potential energy formula, okay, MLV or MLF. Okay, and remember, guys, the letter kind of tells you where you're supposed to use this. LF is used where it freezes. LV is used where it vaporizes. That way they kind of make sense. And the last thing that's going to be on there is a question about applications of latent heat and energy transfers and the water cycle. Okay. We talked yesterday just a little bit about, during our review, how right now, what's the water cycle doing outside? Yeah, it's slowed down. In fact, it's pretty much stalled. The water cycle is not, there's not enough energy right now for our water cycle to get going. So the water isn't cycling. All the water is, it's frozen, it's trapped. Okay. When it gets warm, and we're supposed to get a Chinook here soon, then the water cycle will get going again. Some of that snow will melt, some of it will evaporate. Okay. Humidity will get into the air. Okay. But right now, what does the air feel like? Besides really cold and hurts my face. It's dry. Okay. When it gets cold, it gets dry too, because we don't have enough energy to get water vapor into the air. Okay. It very rapidly, when it is in the air, condenses, freezes, and just deposits on the ground. All right. So right now, in a cold area, the water cycle can't get going because latent heat involves a lot of energy. It takes a lot of energy to change the state of water, whether you're changing it from a solid to a liquid, or more so from a liquid to a gas. Okay. So there'll be a question that asks you to kind of apply your knowledge of that idea. Why does the water cycle not go when there's not a lot of energy? Okay, how does that have to do with latent heat? That kind of thing, tying those together. Okay. Oop, that's weird. Okay, and then there's the last thing, biomes. Okay, there's some multiple choice questions, obviously. Picture and description of a biome. You have to identify it. It's all in color, so the pictures are pretty straightforward. Just remember, don't rely strictly on the picture. Okay, we saw yesterday when I showed you the first picture for the prairie that it didn't look like a prairie. We saw just a couple of pieces of grass and a bunch of thistle and cactus. Well, sometimes on the prairie it can look like that. But we might think, well, that's kind of desert looking if we only looked at the picture. But if we read the description, it'll become pretty obvious. Well, it's not desert. Okay, it says there's lots of grass and more rainfall and things like that. Everybody with me on that? Okay. All right, so on your test, there are whoops, wrong test. Okay, so on your test, there are 25 multiple choice questions, right? And they covered, there's a few things that are application kind of questions, but mostly it's recall. So there's, like we said, some biome questions, some questions on the water cycle, some questions on factors that affect climate, some questions on heat transfer, conduction, convection, radiation, okay, applications of that, and a couple of things on latent heat. Okay. And then there are 9 written. Okay, and as we said, one of those questions is here's a climatogram, tell me what biome it goes with. One of those questions is here's a location, talk about the factors that affect its climate and what its climate will look like. There's one about global wind patterns. Okay, there's one about kind of prevailing winds. There's one about energy, actually two about energy transfers, specific heat problem, latent heat problem, and that one I talked about that had latent heat in the water cycle. Okay, those are your 9 problems. All right, so that should give you a pretty good idea of what kinds of things to look for. Okay, so the review sheet, guys, is posted in the stream for you. Okay, just click on it. It's a Google Doc. Okay, it'll open up, and that's what you'll see. Okay, there's practice questions, some activities there for you to do that'll help you to prepare. Okay,